Well, good afternoon. My name is Antonio Gómez Corral, and I will chair this session in Madrid. Well, first of all, welcome to the 7th edition of Diderot Mathematical Forum, an event organized and coordinated by the Recent Public Awareness Committee of the European Mathematical Society, jointly in this edition with Université Paris Descartes, Politecnico di Milano, and Universidad Complutense de Madrid. Well, to begin with, it is a pleasure to introduce Professor Antonio Díaz-Cano, the Dean of the School of Mathematics, who is going to say some few words. Please, Antonio.
Thank you, Antonio. Good evening and welcome to the Faculty of Mathematics of Universidad Complutense de Madrid. It is a pleasure for me to welcome also to the people who are following this Diderot Mathematical Forum by streaming. I want to congratulate European Mathematical Society for this interesting activity. I would like to recognize the efforts and dedication of all organizers in Paris, Milan, and Madrid. Especially, I'd like to thank Professor Antonio Gómez Corral and Miguel Angel Herrero for the organization of this session in Madrid, and to Javier Cima de Villa in charge of the technical details. I'd like to thank to all the participants in this forum. Just to say only a few words about the faculty, we have around 25 research groups in the faculty, and one of the strongest research group is led by Professor Miguel Angel Herrero, who is the following plenary speaker, and I am sure that all of you will enjoy his talk. Thank you very much.
Well, let me introduce Miguel Angel Herrero, the second plenary speaker in the afternoon. Well, he is a full professor of the Department of Applied Mathematics in the School of Mathematics. In 2014, Miguel Angel Herrero was appointed EMS lecturer, becoming the first, and so far the only Spanish mathematician in the list of lecturers of the European Mathematical Society. Well, I may also mention that among other positions in scientific societies and editorial boards, Miguel Angel is an elected corresponding member of the Spanish Royal Academy of Science. Miguel Angel is an internationally recognized expert in differential equations from both the theoretical perspective and practical use. He is currently interested in the interplay between mathematics and biomedical problems, and in a more general setting, mathematical modeling, simulation, and optimization in natural and social sciences. Today, Miguel Angel Herrero is going to talk about mathematical models in biomedicine.
Thank you. Can you hear me? Okay. Thank you, both of you, and thanks to everybody for being here. Let me just go straight to the subject of my talk. I wish to make some remarks on mathematical models in biomedicine, certainly, because this is the title of the talk and the session. But I wish to stress a particular aspect of my approach, which is looking for simplicity. And this is encode, and this title, Simpler is Better. I'll try to explain to you in the sequel what I mean by that. So first of all, we are talking in this session about mathematical models of biology, in medicine, and the first question that comes to everyone's mind is, really, is that possible? I mean, isn't that biology is too complex for mathematics? There's a general caveat that comes to many people's mind when dealing with this kind of issues. And let me just remind some excerpts of an article which will be quoted in the next slide, which begins like this, begins talking about airplanes. And the authors say a particular type of aircraft, Boeing 777, is a truly flying circuit with over 150,000 different modular subsystems organized through non-trivial protocols to give rise to a complex control systems network, which includes more than 1,000 computers on board. Actually, the level of internal activity is staggering. For instance, the data recorded on the state of the aircraft during its final test amount to a human genome per minute. So this just is a remark to hint at the fact that complexity in itself is not the main issue, because in these days we are in a position to deal with very complex systems, like, for instance, this type of aircraft. The real issue is that living beings have properties that are absent in inorganic matter, which are basically purpose and function. Living systems, as is written there, certainly obey the laws of physics and chemistry, but the notions of function or purpose differentiate biology from other natural sciences. In particular, what really distinguishes biology from physics and survival are reproduction and the concomitant notion of function. So function, purpose are the characteristics of living beings, of the real life, that make it a real challenge for modelers and for anyone interested in dealing with them. So how could we possibly understand function and purpose? Should we just rely exclusively on experiments? Certainly, experiments continuously unveil large amounts of data. However, as the gentleman with the curly hair in this slide remind to us, it is wrong, he said, to try founding a theory only on magnitude that you can observe. As a matter of fact, he said, the very opposite happens. It is the theory which decides what we can observe. Well, whatever you think of that, this is what he said. And what I just wish to add to that is that models, what we call mathematical models, represent or best try to understand what lays hidden beneath huge heap of facts. It's like trying to extract a shape from which is hidden within a stone. This is precisely the way Michelangelo Buonarroti thought his art was. He several times said, all I want to do was to try to extract something which lies within the rock. And this is what we try to do with mathematical models. How many details should be kept in a model? And you have two different alternatives, two different scenarios. In one, you have plenty of detail, and it's certainly a masterwork, there is no question about that. But on the right, you see something much simpler. And it's difficult to decide which of them really has more artistic appeal. I mean, it depends on different persons, I guess. Somehow they illustrate two different alternative choices. So, we are then in a crossroad, and we have to decide, should we go complex or simple? Don't worry, I'm not going to follow this way. I'm just trying to show you a few equations so that you can see that some people, actually clever people who know their business, use them to obtain interesting results. So the seemingly obvious path consists in building up models which are as comprehensive as possible, so that many, perhaps all, hopefully all, biological ingredients will be included therein. And in this way, you can get very large systems of equations. You can count 7 of them here. There are some more, some extra equations, and the slide to come. And this is taken from a paper by Pisua Belmonte and his group on a particular aspect of pattern formation in developmental biology. So this is one thing you can do. You can try to keep track of every single aspect in the phenomena you want to understand better, or you may think twice and look instead for the simplest possible explanation. This is, again, some sentences taken from a work by a famous developmental biologist, John Tyler Bonner. And he said that, you know, even when you deal with simple, quote-unquote, simple organisms, the more one delves into their mechanism, the more complexity emerges. One may argue that details are development, but I will take a different look, he said. He can afford to do that because he is a very famous guy. It seems to me that there are some basic principles that underlie all details, and it's precisely upon them that the details rest. So now, after this kind of introduction, let me just try to go for a particular case, a particular example, to illustrate what I was explaining in a general way before. So now, let me just focus on a particular situation in immune response, a subject which has been already addressed in the morning, so I can really take help from my colleague in some of the aspects that will come afterwards. So let me just go for that. So the subject is immune response, and the plan, a very broad plan, is can you possibly derive or can you explain the global strategy of immune system cells fighting a pathogen, taking into account, and this is key to what follows, that any of these cells can a very limited set of choices only. I will insist on this in a minute. There are some keywords and some basic tools, which I will explain afterwards. Let me just say that this is part of work with a number of people who quoted here, but paramount about them is my colleague Clemente Arias, who is now currently in this School of Mathematics as well. So this is the second time you see the word immunology in a nutshell, so it's 2 nutshells already, right? It's much better because you can cover many more things. So just to go rapidly over it, so we are dealing with immune response, and by this we mean an efficient evolutionary strategy to meet challenges posed by infectious agents. And key players, not the only ones, of course, but key players in this immune response are Tcells, which have been already talked about in the morning. You see some pictures here, just to make you sure that these things are real, right? At least there are pictures of them, which is not exactly the same as meaning that they are real, but there are pictures of them. And the mechanism of T-cell activation was brilliantly described this morning by Mario, so I just will go very quickly over that. The thing is that there are these so-called naive T-cells, which are kind of sleepy, as perhaps some of you are now. And they are, you know, going here and there, waiting for a purpose, let's say. And in some cases, they can be activated by some messengers called dendritic cells. And what they do is, these dendritic cells, they display small pieces, peptides, pieces of materials, let's say, from infectious agents or from whatever origin. We call all of them antigens in general. And they display them and show to all these naive cells saying, hey, do you recognize this? Have you ever seen this, something like this before? And then this is interesting. There comes a key and lock mechanism. So some of these naive cells say, well, I don't know. Can I see closer? And they show the antigen, which is a kind of key. And the cell has in its membrane what we call a receptor, which is a kind of lock. So if the key goes badly into the lock, try a little bit, they say, no, forget it. You can't go any further. I can't recognize this, sorry. And the cell with the key, unused key so far, keeps on going, looking for another cell which could possibly recognize this antigen. If this happens, if at some point this key matches well with some lock, then they get together, both of them, for a long period, and they give rise to what is called immune synapse. And then a number of things happen. So this will be described immediately. Just to give you an idea, think that in some animals on which experiments are easier and more comfortably done than in humans, the number of cells that at any given moment of time can recognize a given antigen is very little. In mice, for instance, about 200. So you have to find one of these 200 cells, which is not so easy. They are very small, they are distributed to the blood system and so on. But if you find one of them, then something interesting happens. A very active and efficient army is recruited immediately. So when this immune synapse is efficiently done, these T-cells activate and differentiate into effector T-cells, which are extremely efficient warriors, ready to fight any invasion, like this guy here, right? Moreover, they undergo massive proliferation. They start reproducing very fastly because they need lots of them to check the invasion, right? And in a very short amount of time, they multiply their numbers by millions. So you have millions of these soldiers ready to fight, very, very courageous. It has never been said that any single T-cell was a coward. All of them fight to death, the invasion, right? Which is not actually the case with standard soldiers, of course. But this phenomenon of having, going from a very small initial number of cells to a large number of activated T-cells is called clonal expansion. And an interesting thing comes afterwards. So in many cases, the invasion is won, and then you end up with a lot of soldiers that are no longer useful. They are not longer needed for any purpose. What you will do? Well, humans will demobilize them. Cells kill themselves. They die. They undergo apoptosis, which is a kind of suicide. And in this way, they restore basically, not quite, but basically, the initial number of cells which were circulated there, plus some extra number of memory cells, on which more will be said later. And the interesting thing is that this happens many times in our lives. Most of the infections we get, we never get aware of, because they are fought and won by this mechanism. And there is no central command giving orders. There is nothing like headquarters where some general of T-cells says, you should do this, you should do that. No. This is a kind of anarchistic army. They do everything by themselves. They decide by themselves. And the only thing that they may decide, each individual T-cell, is they have a choice between dividing or dying. I wish you to have a look at this picture, because this is the key issue I wish to deal with in this talk. There are many things that can be said about immune response. Some of them have been already addressed in the morning. Many more things could be discussed, but let me just focus on one particular single aspect. It is the fact that clonal contraction occurs, and intriguingly, it is a delayed effect. what I mean is the following. If you look at this picture here, you will see two axes. Horizontal axis is time, and vertical axis is number of cells. And what you have, initially you have a pathogen who is coming, right? And after the pathogen is in, so this effector Tcells get started and ready to fight the invasion. But the interesting thing is that, as you can see in this picture, and what is observed over and over again is that the expansion, the increasing of this army of effector Tcells, the soldiers, continues to occur even when most of the pathogen is already gone, is already destroyed. They keep on going. There is a delay. You will see two maxima here, right? There's one maxima here, another maxima there, and you will think that, well, in an ideal world, they should coincide. They will, the pathogen will trigger an invasion, and at the same time, the maxima will be achieved, and then the effector Tcells will be demobilized. But what is observed actually is that there is a delay, right? So that activated cells continue to divide even in the absence of antigenic stimulation. Why should they do that? There is no one giving orders. They do it by themselves. They decide by themselves. And if they decide by themselves, how comes that they always decide the same thing? This is related to a kind of microscopic description of what is going on, which is something contained in the sentence at the beginning of this slide. Cells have to make individual decisions in confusing scenarios. You have here a painting, a famous painting by Peter Bruegel, where you can see many things going on. And actually, most of the things that are going on are not very nice, I must admit. But, however, if you happen to be in this lower right corner, and you have a good sight, you could see a young gentleman playing guitar from his fiancée. So life is nice there, but not exactly the same in other parts of the painting. So every cell has to decide what to do, and has to decide if the infection is very active, and then you have to fight them no matter what, or if you can really forget it and demobilize in this very sharp way, just by killing itself. So now let me search for a minimal model to account for this phenomenon. And let me stress this, I'm not making any, in this moment, it's not my aim to make any general theory of immune response. I'm just trying to explain to you, if possible, how comes that this response is delayed? How comes that cells that have to decide by themselves, exclusively by themselves, not following any order, do so in such a particular way so that they continue dividing even when they are no longer needed? And to do this, what we will do is to select this, the plan is to select the small number of assumptions based on hard facts needed to account for the phenomenon considered. Then we'll try to put this assumption in a quantitative manner, and we'll try to solve or simulate the corresponding system of equations and see what happens. See what can we get for these solutions. So now the question is, what is the simplest model that can account for this delayed clonal contraction? Well, I don't know, actually. But all I can do is to try to present you a simple one. Could be even a more simple one. Is I cannot rule it out. But let me just go with the approach that we follow with Clemente and some other collaborators in this work. So the first thing is try to select the smaller number of assumptions that you need to account for the phenomenon you want to consider. And then we come at the first of this assumption. And the first of this assumption can be stated like this. Any single cell, any single of these soldiers, remember the Chinese soldiers ready to fight, right? Any of them is really wanting to do one of these two things, either to divide or to die. And the only thing, that makes a decision not completely straightforward, completely immediate, is that it's the competition between two inhibitory molecules which determines the fate of each of them. Let me give you an example. Well, first of all, these two molecules have names. They are called retinoblastome and BCL2 proteins. They both were first identified in tumors, because in tumors many things get overexpressed. But afterwards, it was found that they are present in many other cells, and normal cells, or living normal lives, let's say. And the thing is the following. Any of them is able to inhibit something. Look at the picture number A and the left of the pictures A. You have an horizontal axis is time, vertical axis is number of molecules, right? And then you have two concentration of these two proteins, BCL2 and RB. And you will see that RB disappears or goes below some threshold before than BCL2. So the first inhibitor, first of these two, RB, disappears before than the second one. And then this means that the cell has decided to divide. And then it starts division. And you cannot stop this. You can kill the cell, but you cannot stop it from doing that, right? Conversely, you go to A in the right, you will see that here BCL2 is the first one which disappeared. It's used up. You can think of them as fuel, right? One of them is used up, then some process starts. If BCL2 is the first one to be used up, then the cell starts killing itself, and you cannot stop it anymore. The decision is made. Any of these two decisions are irreversible, right? Of course, depending on the amounts of these substances, the duration of these processes may be longer or shorter, right? But the idea is the same. Any of them has these two inhibitors. The first of them which disappears decides what to do. That's it, okay? Now you might say, well, how much, what is the amount of these inhibitors that they have? How can you estimate this? Well, then you go to the second assumption. I already mentioned assumption one is very well established in our standard knowledge. Same happens with assumption two. It's the feedback among membrane receptor which controls the dynamics of these two quantities. So the idea is that the cell is like one of these aircraft of Star Wars, right? They have some receptors, some entrances. And receptors provide a mean to communicate with the outside world. Through these receptors, information comes in, which determines the dynamics of any of these two inhibitors. And on the other hand, there can be feedback among receptors. Some of these receptors can talk to each other and say, look, we should do this, because I feel that I have to do that, right? So receptors provide an entrance, or an exit. It's a communication to the outside world. Most of the substance that eventually get in to the cells don't do it directly. They have to go through some receptors and trigger some kind of reactions which eventually produce some effect inside. They are too big to go straight through the membrane. Right? And then it's the interaction between cytokines, some chemicals that flow around the cell, and receptors which control not just the evolution of these inhibitory molecules, but that of their receptors. And there is a third and last assumption. We only need 3 assumptions for this game. This assumption says that these naive cells, which were lazily looking around waiting for someone to excite them, once they get excited, because there is this immune synapse that says you have to start mobilizing and fighting the invaders. Once they get activated, they will divide. But they do it in a very peculiar manner. Let me just skip this. The first time they divide, they do it as in B in this slide, in an asymmetric manner, meaning that the parent produces 2, let's call them daughter cells. One of them is exactly like the parent. So it's what I will, this is to be taken with a grain of salt, but these are kind of stem cells, pluripotent, able to do several things yet. But the first time that they divide, one of them gets exactly the same prerogatives that the progenitor had. The second one, this one with the black spots inside, is ready to fight. So the division is asymmetric because the 2 cells resulting from this division are not equal. One is like the parent, the other is just ready to fight. After that, divisions are symmetric. They produce more and more fighters, ready to go to the front line, okay? Now, we have to put this in a way of modeling. For this purpose, I have to ask for advice from my colleague in this slide, who raises a very significant question. They say, well, you have to put, you said, you have to put basic assumptions in a quantitative manner by means of a simple set of equations, but how can you tell an assumption which is basic from one which is not? How can you decide which is basic and which is not? Well, this is where modeling comes in. And then you may go back to this crossroad we skip carefully in the beginning and say, well, you know, there is a lot of molecular circuitry, and you have here a painting, a slide where you have many molecular circuits which have been already identified and looks really awful. So how can you model this in a simple and convincing way? And the idea is just summarize a little bit. So instead of using the model, you have the very complex, exceedingly complex molecular circuitry, which is depicted in the left. You just replace this by simple machines. You have some kind of washing machines. You put some balls in, which is the signals that come from outside, and they do something. Something is probably described in the left, and eventually they produce some red and blue balls which play the trick at the interior. These are the substances which will meddle with the inhibitors and eventually decide which of the 2 actions is got to be taken, right? So what you want to do was, I mean, at this moment, at this juncture, perhaps the easiest way is to use differential equations. And then you use differential equations for 2 things. Basically, for the concentration of 2 substances, which are these inhibitors I was talking about before. So C of T is the inhibitor of cell cycle. If you have a lot of them, then you don't reproduce. And A of T, the inhibitor of the apoptosis. If you have plenty of that, you don't die, if you're a T cell, right? And these quantities change in time according to feedback from receptors, which are these R1, are key over there, and also according to a stimulation by the antigen. The antigen is this R sub capital T, which is, the invasion. This is the invader, right? So I could say this, what we have in mind is this kind of washing machine system on the left, but we want to represent it by differential equations which are more respectable, let's say, right? And not only that, they are easier to be used and to draw conclusions from. let's go even more simpler. Let me say that linear feedback might be, and in this case, is better. And linear equations too. So I try to go linear as much as possible. And there are some arguments for that. And one of them is that, as depicted in lower part of the slide, and if you have some linear response to stimuli, then you always have that the same amount of stimulus produce the same result, independently of the order in time in which it is acted upon. You want even more simpler, just two types of receptors. One type for death, the other one for division. Meaning that we are concentrating the information coming from the outside world, which is relevant for the cell cycle inhibitor, in the cell cycle receptor. And the same for the apoptosis one. So they have special channels, like in the radio stations. Everyone has this frequency, let's say. And these two types we call proliferation and death. And you have some system of equations which are linear so far, right? And then you have a model, at least at the level of any single cell. You put initial values regarding the concentration of the inhibitors in a single cell and on the amount of the receptors. And then you can simulate this and see what happens. And what you see is that this asymmetric division that happened for the first time divides the population in two categories, the mortals and the immortals. Let me just discuss shortly what is the fate of the mortals. Mortals are the soldiers, which are ready to fight. That is the apoptosis-sensitive lymphocyte. And what you have is that you end up with a system of very simple, ordinary differential equations that you can integrate by hand, and you will. And the interesting thing in this system is that you will see, let me just describe in detail one of these systems. I will skip the remaining ones. What you have here in the first equation is that C of t, the amount of inhibitor of cell cycle, is removed by information coming from the proliferation receptors. Same happens with the apoptosis one. And then you have two extra equations for the receptors, for the holes in the membrane, right? They are proliferation and death. And there is something interesting here. Proliferation receptors are stimulated by the antigen in the model. But proliferation receptors, the fourth equation says, also stimulate the formation of the death receptors. And you would say, how comes that? Why is not the other way around? We don't know, but this has been observed, and the other way around, no. So this is something which takes into account something which is observed, right? And then you can scale and resolve these things, and you find two times: the time to kill yourself and the time to divide yourself. And the cell decides according to which one of them happened first. So any lymphocyte, and you can see an explicit solution of this system, any lymphocyte will eventually divide if the corresponding time for being killed by apoptosis is larger than time to replicate, and the other way around. So the fate of the mortals is to divide and then die. Because as you are, after any round of division, you are using up your inhibitor of death. So after a few rounds, you get rid of it. And then the cell will kill itself immediately. No question, no more divisions. This is what is illustrated in this series of transparencies. And is recalled in famous and sober verses by Homer, the Greek poet: as the generation of lives, so are the generations of men. Well, in this case, the generation of Tcells. What is the fate of the immortals? The immortals are those cells coming for the first asymmetric division, which are exactly, we share the same features of the parent cell. These don't have death receptor stimulated, and then what they do is to divide a number of times and then to have some rest. In this manner, they perhaps increases slightly the original pool of naive cells which were available, but are now activated and have memory of this invasion. So if the invasion comes back later, the same agent comes back after a few weeks or something, they are there and they can remember and they are ready to fight. So this is illustrated in this picture. So these cells which are immortal at the time scale of the process being considered. It is not that they never die. They will be disposed by some other agent after a while. But in the time scale of the pathogenic infection, they are effectively immortal. They can divide a number of times and then stop dividing and remain there. But so far so good, but this is only individual behavior. How about the outer world? Well, the outer world is very important, and it's actually from this global coupling that an emergent response comes. What we say is that we postulate that there is some pathogen and Tcells around. You may call Y of T the concentration of pathogen and N of T the concentration of Tcells. You can postulate a simple way of interaction by population, one of the simple population dynamics models, saying that, Tcells remove the pathogen, right? And the antigen goes into any of these cells, and when they divide, the number of receptors which have been activated get distributed into the daughter cells. You can postulate several possibilities. The easiest is, 50-50. Half of the receptors go to one of the daughter cells, half of the receptors go to the other one. But the important thing is that the global coupling comes now from this equation, and of course, the way in which it's implemented after each iteration is illustrated by the other equations. And now we are finishing. So this transparencies, this slide, this one in particular summarizes what we see. In the left, these are data from different infections and what the model yields. The model gets things more smoother because when you represent something which is numerically simulated, you usually smooth it out, right? And you can compare, you can consider also the influence of some kind of noise acting in some ways. For instance, you may decide that it's not always true that 50% of the receptors go to any of the daughter cells. It could be 60 and 40 or something like that. But what you get is something which is reminiscent of what was written in the slide before. You get the delayed effect on the clonal contraction. And you get this only out of a very limit of choice of any T cell. She can only divide or die. And she will do it according to the first of these two inhibitors gets used up. And this in turn is related with input from the outside world. But that's it, right? There is nothing else. Now, let me just thinking about finishing, right? Some caveats, some things to be considered before concluding. Caveat means careful, right? So that model was simple. I said, I cannot swear that this is the simplest model, but it was simple enough. But will the simplest solution be the one selected in the course of evolution? Because this hasn't happened from one day to another. This system has evolved along with time, and probably there have been several ways and several directions taken. How can we make sure that the simplest solution is selected? Well, I don't know, but I like to take this sentence from the work by Daniel Bernoulli, which was quoted by Mario this morning. He said in this this wonderful essay he wrote about the influence of the inoculation to fight smallpox, viruela. He said, to this day, we know of no observation that compels us to withdraw this assumption, since, he said, the simplest laws of nature turn always to be the most likely ones. Well, this is what he said, right? But I'm just reminding it. That's Daniel Bernoulli's word, not mine, right? How can you tell that the simple solution is unique? It's another way of going to the same question. Well, we don't know. Actually, in many cases, it's likely not to be unique, because in the course of evolution, as I said before, probably several different things have been tried, and some of them may have been retained. That is what they call redundancies. There might be some systems working in parallel, or some fossils of these systems being retained. We don't know, right? And there is a very serious one, just to conclude with these remarks. How about model parameters? Well, discussing about parameters have been a recurrent issue in these talks, and talk by Marie in Paris and talks in the morning. Parameters are always the crux of a model. It's a question, a fact that you learn with time, when you work with people in really applied sciences, is that the problem is not so much with the models, but with the parameters. There are many models that can fit whatever you wish. But the important thing is that you have to select something which is sensible, and if possible, you have to reduce the number of parameters to a bare minimum. And moreover, and last remark, it's important if these parameters are structural, something that you can measure experimentally, something like how is the answer of this lymphocyte of this particular input of substance, right? Now it's time to say that the end crowns the work, and this image is just to remind to some of you that feel a bit sleepy that you are perfectly right to do so. I mean, it's a natural feeling at this time of the afternoon. So thank you very much for your attention.
Well, thank you for this nice talk. Well, there is a delay in the transmission, so we are going to wait for questions by using the Twitter account of the society. So we start with questions from the audience. So please, the first question. Yes.
It's too far, this guy.
Soy el pesado de la conferencia. Bueno, a question. I didn't get exactly why do we see the delay.
Sorry, I can't hear you very well. So
I didn't understand why we do see the delay in the creation, in the creation of Tcells. The delay you mentioned. Why do we see it?
Well, we see it because it's there. So the delay is a fact, and the only thing we can do is to use a model based on facts which are known to hold, and see that the model reproduces this delay, and moreover allows you to estimate some quantitative issues concerning the delay. But the delay is there. We don't explain it. We just try to understand what agents give rise to this delay. And on a more general level, you could say, well, the delay is probably a consequence of the fact that there is no central command. And cells have to decide by themselves and take individual decisions and from the individual decision you get an emergent picture, and building out the emergent picture means some delay. But this is a kind of interpretation, right?
Yes, please, more questions? So, well, we have a question in the Twitter account. The question is as follows. What about spatial effects in immunology?
Okay. Well, the spatial effects are important in immunology and elsewhere. But in this model, what you are looking is a particular piece of the tissue of the region where something is happening. So spatial dependencies is ignored here. You always are working with average quantities.
Well, the next question, please. As I check the Twitter account again. Well, I have a question for you. You had been talking about two options for a cell. The first option is to divide, and the second one is to die.
Yes.
Well, I guess that there are other options in reality. So I would like to know if you are able to incorporate these other options into the model.
Mm-hmm. Yeah, there are some other options, but not too many. For instance, the most interesting option, which is not included here because there is no need for it, is that cells may also differentiate. So they can divide, they can die, and somehow they can say, well, I'm happy with the kind of life I'm having, so let's change into another thing. And they can differentiate into different phenotypes. And moreover, they can also differentiate back, and this is really amazing and a rather new fact, something which has been proved only recently and with some restrictions. But let's say that for practical purposes, the choices that any cell has, any general cell, talking in epithelial cells or mesenchymal cell, is dividing, dying, or differentiating into a different thing. Mm-hmm. Not anything, but many things. There are several paths that are open for differentiation.
Yes, here.
Previous slide, you have shown some noisy simulations.
Yeah.
What sort of model have you used for that?
Sorry?
What kind of model?
Yeah, in the same model, you introduce some noise. For instance, you say, what happens if, instead of having these fixed values, you introduce some fluctuation about this.
Okay, so you add some noise to the equation?
Yeah,
okay.
Things like that. And you see some noise.
Yeah, sure.
But nothing really, significant, let's say.
Well, a new question was sent from Paris. The question is, what is the link between the delay and the cell cycle duration of the two types of T cells?
Well, the delay is not so much linked to any individual T cell cycle. T cell cycle duration depends on the amount of inhibitor available for the cell. So if the cell has a lot of cell cycle inhibitor, then this cell will not divide. It will take a lot of time before she thinks seriously about dividing. So this is an internal thing. So the delay emerges from the global coupling, from the global response to the general situation. And this general situation usually corresponds, and that's perhaps an interesting point to be made, to a kind of local equilibrium with cytokine, with chemical signals concentration around the cell.
Well, more questions from the audience? Yes. Just a second. The question is coming. Yes, please.
Thank you for this nice talk. I have a question that has to do with the response time. The response time of the immune system. you have shown that there is a delay in the Tcells, but for me it's very important the time the immune system takes to respond to the infection. This is the beginning. Do you have some results about that, or how to think about
No,
that?
in this talk, the only thing I wanted to concentrate is in how to explain this interesting feature, saying that, well, you know, the cells continue to divide, even when they are no longer needed. Why? You are using a lot of resources, metabolic resources, things. Why do you do that, right? It will be going back to this, take one of these pictures, for instance. Well, actually, the one in the bottom. Forget about these fluctuations, right? So you have the pathogen raging, and when the pathogen is raging, the effector T cells are beginning to grow, but they continue to grow a lot of time, comparatively speaking, afterwards. So why is that? Well, we don't know. The thing is that this is something you observe, and what is true is that in a way it's a kind of metabolic loss, because you have to produce a lot of cells which eventually will be destroyed. But on the other hand, it's important to have this efficient response in the absence of any kind of central organ on command. It's not that like headquarters say, you do this, you do that. There is no coordination. And what you lose in one hand, you gain in the other. So you don't need this central organ. You will respond to this. But the cost is this delay, right? This is a way of interpreting. I don't know if my colleague Clemente will agree with that, but it's a way of making an interpretation out of it.
Maybe it's a way of being sure that the pathogen have disappeared. So
Yeah,
it's a
sure.
matter of
I mean,
security.
in this way, it's fine. But the thing is that you are somehow you are spending some energy, some effort, and some cells, some good and brave fighters that eventually had to be first created and then destroyed, which is a pity. I mean, they don't deserve that. They don't get decorated, actually. It's really a shame.
Thank you.
Well, I think that you have more questions from the audience. Well, so it's time to finish. Let's thank again to the speaker for this nice talk. Well, this is the end of the second plenary session. Remember that the next plenary talk will be transmitted from Milan at 5:30. 5:30. So, merci beaucoup, grazie mille, gracias, thank you for your attention, and goodbye from Madrid.